welcome back to the lecture series of finite volume series, and we are in the middle of our discretizations of convection diffusion system, and so far we have looked at different kind of discretization scheme like upwind, central difference, second order upwind, downwind, quick scheme and Form scheme, and we have analyzed their stability, accuracy and everything. So, now we can look at that there are certain issues, or rather I would like to say there are couple of errors which may arise due to discretization of the convective term. One is the diffusion error, another is the dispersion error. Now, there are always a trade off between your higher order scheme and the less stable scheme. So, one case it provides stability, but it is lower in accuracy, other case it is more in the error prone for the dispersion kind of error prone, but it is higher order system. So, the idea is that which will actually give us a platform to find out some scheme which is of higher order accuracy, but at the same time it is stable. I mean, in the sense it should not give you any sort of small wriggles or oscillations where the sharp gradient occurs. So, we will look at the higher order schemes now and how to actually formulate those schemes from the basic information. That is what we will discuss today. Now, before we move to that, one important information or the topic that we started discussing, but we could not finish in the last lecture is the deferred corrections approach. So, we will first talk about that and then we will move to the higher resolution scheme or higher order scheme with better stability. So, the deferred correction approach, it is essentially what it does, that it enables to use the higher order scheme and easily inside this formulation. So, this is also applicable for unstructured and structured grid. So, there is no restriction on the grid. Also, this method is based on the calculation of the convective flux. So, the convective flux at phase F, which is calculated using some sort of blending of the higher order resolutions and the upwind resolution. So, the way it is formulated is that m dot f phi f at higher order is m dot f phi f from upwind plus m dot f phi f higher order minus phi f upwind. So, here U stands for upwind scheme and HO stands for higher order scheme. So, it is essentially a blending function of upwind scheme and higher order scheme. So, what it does that when you get these things, the first term of this equation, this can be calculated implicitly and the second term which can be calculated explicitly. Okay. The reason is that why can be calculated can be implicitly, it because it can be expressed in terms of nodal values. So, in terms of nodal values this guy can be expressed, and the other one has to be evaluated explicitly, the second term on the right hand side, because at the latest available phi values from the previous iteration, that is going to be used in this iterative process. Now, in terms of nodal values, this equation can be written as m dot f phi f higher order system m dot f 0 phi c minus m dot f 0 phi f plus m dot f phi f higher order minus m dot f 0 phi c plus m dot f 0 phi f, which will get you flux C f phi c plus flux f f phi f plus flux V f. So, this term again is a implicit term, this is the term which is explicit term, where one can see the flux C f is m dot f 0, your flux f f is minus m dot f 0 and flux V f is m dot f phi f higher order minus flux C f phi c minus flux f f phi f. Now, substituting all this information in the convection flux, and then what we will get the algebraic or the compact form of the discretized system like A c phi c plus summation of capital F goes over n b c A f phi f equals to B c, where coefficient A f is flux f f, which is minus m dot f 0 and A c is summation of small f goes over all the faces flux C f, which is goes over all the faces m dot f 0, that will get you, it is the integration over all the faces m dot f plus minus m dot f 0, it is nothing but minus summation of capital F goes over all the neighboring elements. So, A f plus f n b c m dot f, that is what A c is, and the source term which will look like q c v c minus f goes over all the faces flux V f. So, that is essentially we will have the correction term due to deferred correction. So, this is q c v c minus f n b c m dot f phi f u. This is the term which actually is represented as source term due to deferred correction. So, this term one can see is an extra term which arising due to the deferred correction procedure. In top of that, this deferred correction technique results in an equation for which the coefficient matrix is always diagonally dominant, since it is formed using the some sort of an upwind scheme. So, the compacting procedure is simple to implement. However, as the difference between the cell phase values calculated with the upwind scheme and the calculated with higher order scheme becomes larger, the convergence rate diminishes. So, it essentially is a blend of upwind and higher order scheme. So, that is why there is a convergence rate is bit slower or bit lower, one can think about that way. So, having said that, when we talk about all these things, the two issues which are very pertinent is that when you discretize the convection term, these are, one is that numerical diffusion, other is the numerical dispersion. Now, this is more prone for higher order schemes, because the diffusion would be less. So, less numerical diffusion, but due to dispersion, wherever the solution, like we have seen the when there is a sharp gradient, the solution become some sort of an oscillatory nature, and then it goes like that. So, this is a problem of the dispersion error which will arise in primarily second order upwind, quick, from scheme, all the CD scheme, because they are at the spatial accuracy is higher. So, they are not stable when there is a sharp gradient. So, it is essentially due to the stability problem of these different schemes. So, one hand these are highly accurate because spatial accuracy is higher like second order or third order, but at the same time they lead to some sort of an wriggles or oscillations when there is a sharp gradient in the flow field. So, that is one problem. Other hand, dissipation will come from the lower order scheme or the first order scheme. So, but that case less dispersion, which does not mean that the dispersion error would be completely absent in the lower order scheme. We have already seen while doing the analysis for the upwind scheme, we have seen that the value of the k where the both real and imaginary part actually exists. So, which immediately tells these lower order schemes are prone to have both kind of errors, both diffusion and dispersion, but diffusion is more dominant because their spatial accuracy is less, and that is what come from your truncation error. So, when you use lower order scheme, they might not give you this kind of oscillations or wriggles along the sharp gradient, but the solution will smear out like that. So, this will happen with the lower order scheme. Because of the diffusion, things become much smoother, and then it goes away from this capturing of this particular gradient. So, these are the problems. One hand you want higher accuracy, but at the same time you want stability. So, these are the two pertaining questions that one has to answer, that one hand accuracy, one hand stability. So, higher order scheme are accurate, but not very stable. Lower order scheme, they are not accurate, but more stable. So, we need to devise, or rather that actually provides the platform for finding a different kind of scheme or class of scheme which will be of higher order plus stable. So, that is what one needs to find out, and how we can devise those kind of high resolution scheme, that we will see. Now, when you talk about those high resolution scheme, the thing which actually comes is, or they are formulated based on normalized variable formulation. So, which is known as NVF. So, this higher order resolution scheme, these are sort of formed or can be coined using this concept of normalized variable formulation. So, this is the rather the framework. So, one can think about this is the framework which can be used to for description as well as analysis of higher order high resolution schemes. Now, it was introduced long time back. So, what happens in the normalized variable diagram is useful tool. So, there will be NVD which is normalized variable diagram. So, this is an useful tool for the development and analysis of these higher order high resolution schemes. Now, NBF is a phase formulation based on locally normalizing the dependent variable for which the value phi f at phase to be calculated or constructed. So, the approach relies on the upwind scheme phi c, the downwind point phi d, far upwind phi u and this kind of nodes. So, if you see how one can do that, this is your particularly this is the schematic. The schematic shows that there are cell which we are interested, upstream of the cell is u, downstream of the cell is d, further downstream dd, because our velocity direction at that phase in that direction, and far upstream is uu. So, these are used in the structured system for deriving or describing this kind of system. The second picture shows that only C and D and the extrapolated this picture where C and D that are used to extrapolate the variable on unstructured grid. So, this picture shows for structured system and this one for unstructured system, where you can use these cell center values and there will be slightly upstream value u which is in another cell, and at the phase the velocity vector actually moves in this direction. So, one case is structured, other case is unstructured, and the structured case when the phase velocity goes in this direction, this should be considered as upstream condition and the subsequently this side would be downstream condition, and when the phase velocity goes in this direction, these guys would be upstream and this is downstream. So, it just changes the direction depending on the flow velocity direction. So, this is a very useful information and we have come across this information once we started deriving the discretized equation for the convective term, because this problem was not present when you looked at the diffusion term, because diffusion term there is no convection which is associated with that. So, now if you define your normalized variable, your normalized variable such that phi tilde equals to phi minus phi u divided by phi d minus phi u. So, the normalization relation stands for function of u, function of c, function of d, which means it takes into account upstream point, the cell which is concerned of that, the downstream point, and it could be either way around. If flow goes this side, this information will be taken into account, this information also will be taken into account. If it goes in this direction, these are the information which will be. So, this can be transformed to phi f equals to f of phi c, and the normalized value of phi d tilde equals to 1 and phi c tilde phi u tilde is 0, with the normalized value of phi c tilde becomes an indicator of smoothness. So, now if the value of phi c tilde lies between 0 and 1, so what happens? So, it represents a monotonic profile, while if the phi c tilde c is less than 0 or phi tilde t greater than 1, it indicate the extremum at C. Now, top of that, so this you can see how the normalized variable of phi c tilde, which provides this kind of expression. This is shown in this particular graph, where you can see that this particular case which is shown here, this case is the case where phi c tilde less than 0. So, phi c tilde less than 0 indicates that there is a extremum at point C. This is my cell which is concerned, this is the downstream, this is the upstream, and this is the flow direction. So, either it could be extreme maximum or could be minimum, this is what the normalized conditions. Now, the second case, it actually the case where phi tilde c is greater than 1. So, if it is greater than 1, then also you will see there could be extremum at point C. It could be minimum, it could be the maximum value when you consider phi u, phi c. Now, the other case when it lies between 0 to 1, and then this case is the case where it is phi c tilde equals to 1, this case is phi c tilde equals to 0, and this is the case where phi c tilde lies between 0 to 1. So, when it is between 0 to 1, it shows some monotone profile, either monotonically decreasing or monotonically increasing. When it is 0 or 1, which indicates there would be sudden jump in the gradient. So, phi tilde 0 or 1, it means there is a gradient jump. So, this normalized variable actually shows lot of information. What information? It is depend on this normalized value, which actually takes into account what it is lies between 0 to 1, then the profile shows monotonical profile, either monotonically decreasing or monotonically increasing between these points which are used to calculate the flux variable. If it is 0, then there is a jump in the gradient which one can see. If it is also 1, there will be a jump in the gradient. So, these two are sort of equivalent, these two picture, and if it is less than 0, then either of these C value will have certain extreme conditions, 0 or 1, or if it is 1 or greater than 1, then also it represents. So, these are the some sort of an equivalency, whether it is less than 0 or greater than 1, it shows some extreme point on this. Now, since normalization is also useful for transforming this functional relationship or higher order scheme, so now one can use this functional relationship for the higher order calculation. So, which we have already seen that for upwind scheme it was phi f was phi c. So, the transformation will let you have phi f tilde equals to phi c tilde. So, that is the transformation. Now, central difference scheme, we had phi f half of phi c plus phi d, which will transform to phi f tilde, which is nothing but half of 1 plus phi c tilde. So, these are functional relationship which is also or which is true for both structured and unstructured grid, and now for different scheme how it transform to this normalized condition. Second order upwind, the phi f is represented as 3 by 2 phi c minus phi u by 2, which will get transformed to phi f tilde equals to 3 by 2 phi c tilde. From scheme, so that phi f was phi c phi d minus phi u by 4, which will get transformed to phi f tilde equals to phi c tilde plus 1 by 4. Then quick scheme, which is phi f equals to 3 by 8 phi d plus 3 by 4 phi c minus 1 by 8 phi u, which will get transformed to 3 by 8 plus 3 by 4 phi tilde t, and the downwind scheme, which phi f equals to phi d, here it will be phi f equals to 1. So, all the higher order scheme that are based on these nodal values, phi f can always be expressed as a linear function of phi c plus some constant k, where the value of L and k depends on scheme. Okay. So, the point here is that the phi f tilde, this is now one can plot again this phi c tilde in a particular plane, and then the functional relationship of all these schemes will appear as a straight line. So, what we can do, we can look at this plot a phi f tilde versus phi c, and all these functional relationship for different scheme will turn out to be a straight line, and the resultant plot can be denoted as the normalized variable diagram or NVD, on which the functional relationship of all these schemes can be plotted. So, we will stop here and we will continue the discussion in the next lecture. Thank you.